If you still mug up colors, you are doing CFT wrong. This one idea will save 5 questions in JEE. Topper shortcut for crystal field theory. So all these topics will be covered in this particular video. Hello students, let us start Sedgwick's effective atomic number. Once everyone watch part 1 of coordination compounds where we covered till Werner's theory from beginning IUPAC nomenclature. Let us start Sedgwick's effective atomic number EAN rule. So in the complex, whatever complex given, central atom tend to attain configuration like nearest noble gas to get stability. According to effective atomic number rule, central atom tend to attain configuration like nearest noble gas to get stability. Like you see here, helium, neon, argon, krypton, xenon, radon. The respective atomic numbers we need to remember: helium to radon. Effective atomic number minus oxidation state plus number of electrons given by ligands. Effective atomic number minus oxidation state plus number of electrons given by ligands. For example, if I take this one K4FeCN6, for convenience you can write 4K plus and then remaining complex minus 4. Number of electrons given by ligands meaning that is 2 into number of bonds formed by ligands, because each bond can constitute 2 electrons. So EAN is equal to 26 is atomic number, 2 is that is charge of iron, followed by 12 electrons. Why it is 12 electrons? Because 6 cyanide molecules. Each cyanide can form one bond meaning 2 electrons. So 6 into 2, 12 electrons. EAN 36 so follows EAN rule. According to Sedgwick's rule, complex whichever following EAN rule are stable. NiCO4, same 28 it is atomic number, 0 it is oxidation state, 8 here 4 into 2 electrons, overall we are getting here 8 electrons. Follows EAN rule, stable. So next another theory with respect to coordination compounds, valence bond theory. So in VBT, whatever you studied in 11th class chemical bonding, VBT concept is same, just we are applying for coordination compounds. To form coordinate bond, ligand should contain fully filled orbital and metal should contain vacant orbital. See here, ligand should contain fully filled orbital, metal should contain vacant orbital, because ligand donate electrons to metal. Case 1, coordination number 2. Once you recollect chemical bonding VBT, same concept we are applying for coordination compounds. Coordination number 2, sp hybridization, where metal forming 2 bonds with ligand or ligand forming 2 bonds with metal, linear shape, sp hybridization. Coordination number 3, sp2 trigonal planar. See the shape, all are same as it is like 11th class chemical bonding, trigonal planar shape. Case 3, coordination number 4, 2 possibilities, because till here no other possibility, sp2 sp. But coordination number 4, sp3 you can see dsp2, new hybridization, which we did not study in 11th class. Here we are going to see dsp2. sp3 tetrahedral, dsp2 square planar. Shapes once you see, it is tetrahedral shape, square planar shape. For VBT, to find hybridization, compulsory some extra information required. Before that, in dsp2, here important question, dsp2, d used is dx square y square. Out of 5 d orbitals, d used in dsp2 is dx square y square. One question you see here, JEE question. NiCl4 minus paramagnetic and number of unpaired electrons equal to 2. This information given. Find hybridization of complex. So how to find? C. NiCl4 minus 2. Here oxidation state is plus 2. Coordination number 4. Coordination number is equal to number of bonds formed by ligand. Oxidation state is charge of metal. Nickel plus 2, 3d8, 4s0, 4p0. So just we showed regular filling. As they mentioned here, number of unpaired electrons equal to 2. Same condition we maintain, 2 unpaired electrons present. Then leftover vacant orbitals, what are those? S, P, P, P. Hence the hybridization is sp3 for given compound. Similarly, another JEE question. NiCN4 minus 2 given, diamagnetic or number of unpaired electrons. See, diamagnetic information should be given. According to VBT, to find hybridization, we need diamagnetic or whatever information with respect to number of unpaired electrons. So, no unpaired electrons are diamagnetic. Find hybridization of the complex. How we need to proceed? As the specified number of unpaired electrons equal to 0, so here we should satisfy the condition here. According to regular configuration, you will get 2 unpaired electrons, but we should make it diamagnetic, so no unpaired electron should be. So hence, 1 electron transferred here, so here 1 D is empty, S, P, P. So DsP2, so here D is empty, so hence hybridization is DsP2 hybridization. Overall, remember, for VBT, condition must be specified in the question to find hybridization. Case 4. Coordination number 4, sp3 outer D complex, inner D complex dsp3. See, outer D means if D is outside of sp3, outer D complex, if D is inside of sp3, inner D complex. Like this you can remember. sp3D square bipyramidal, dsp3 square bipyramidal. Square pyramidal, trigonal, bipyramidal. See the shape. Here it is trigonal, bipyramidal, above and below. Here square and pyramidal. Okay. If all ligands are same, see the condition. If all ligands are same, then mu net is equal to 0 here. Why? Triangle, they cancel each other dipole moments. Above dipole moment cancelled by below dipole moment. Overall it is 0. If mu net is 0, it is non-polar. Right? Similarly, then if we see other parameters like mu net is equal to 0 means that is non-polar. No doubt, we know already about it. Similarly, if mu net is not equal to 0, then it is polar. See here, mu net not equal to 0, that is polar. Here 4 metal ligand bonds are of equal length like this. Here 3 metal ligand plus above and below. Total 5. 3 metal ligands are of equal length and 2 metal ligands are of equal length. Metal ligand bonds. D used here dz square, very important. Here it is dx square, y square. Information based statements we wrote. Coordination number 6. sp3 d2 possible, d2 sp3 also possible. sp3 d2 and d2 sp3. Outer D complex, inner D complex, because D is inside, here D is outside. For octahedral complex, arrangement like this: metal middle, everywhere 4 square like ligands, above and below 1 more ligand. If number of unpaired electrons increases, spin value increases, because spin formula half into number of unpaired electrons. So outer D complex contains more number of unpaired electrons. Outer D complex. More number of unpaired electrons meaning here more spin. That's what we mentioned, high spin complex. Inner D complexes are referred as low spin complexes. Inner D complexes meaning like here you can see DsP2, D2sp3, such complexes. Close the note. Drawbacks of VBT: it does not distinguish between strong and weak ligand. No concept of strong and weak ligand till CFT. Crystal field theory introduced strength of ligand, but here no point of strong and weak ligand, nothing is specified about it. Every time some additional information required to find hybridization. To find hybridization, according to VBT, extra information should be. So that is the drawback. Without extra information, you cannot distinguish or you cannot find exact hybridization. Okay. Next, the first theory we started with Werner's theory. Second, Sidgwick's effective atomic number rule, EAN rule. Third theory, valence bond theory, VBT. Then fourth one, crystal field theory. Very important, having good weightage for this topic. Okay, see now. Crystal field theory, here ligand as well as central atom are considered as point charges and there is electrostatic interaction between them. According to CFT, ligand and central atom are considered as point charges and there is electrostatic interaction between them. Okay, so here D contains 5 orbitals, we know, dx square, y square, dz square, dxy, dxz, dyz. You studied in 11th atomic structure about shapes of orbitals. Total d orbitals are 5. Okay. Out of 5, here these two, dx square y square dz square present along the axis. Along the axis meaning, for example, dx square y square present like this, along the axis. Dz square, if it is dz, here there is ring here along the axis. But dxy, how it is present, is between the axis present. If it is x and y, dxy between the axis. So here see, lobes are along the axis, here lobes are between the axis. Around 45 degree to the axis here along the axis. For octahedral complexes, first we are going to see crystal field theory, case 1. Case 1 for octahedral complex where coordination number is 6. See, I showed shape of octahedral complex, square type, 4 ligands and above and below. Okay. Now, it is assumed that all 6 ligands are coming along XYZ axis. See here, along. Remember, it is along XYZ axis. As ligand approaching metal along axis, then dx square, y square and dz square experience more repulsion than these three. Why? These three orbitals, their respective lobes are along the axis, here these are between the axis. So, due to more repulsion, energy of dx square, y square, dz square increases. Why here more repulsion for these two orbitals? Because these orbitals lobes are along the axis. If ligand is approaching along the axis, automatically energy of orbital increases. Hence, in the absence of ligand, it is degenerate. All orbitals having same energy. But due to influence of ligand, splitting of energy observed. Orbitals which are present along the axis experience more repulsion from ligand and increases energy, undergoes increase in energy. Remaining three, which are where lobes are 45 degree to axis, their energy sequence, you can say energy of these three orbitals less than energy of remaining two orbitals. Okay. Dx square, y square, dz square we referred as EG set. Dxy, dyz, dxz referred as T2z set. Names they gave randomly, here no particular logic for this. EG set, remember, two orbitals, two letters we used, 3 letters, so 3 orbitals. T2g set, 3 orbitals, EG set, 2 orbitals. Remember like this. Okay. See the representation of octahedral crystal field theory for octahedral complexes. Here there is energy representation, energy increasing in this direction. In the absence of ligand, energy of all 5 orbitals, it is same. You see here 5 orbitals present, all 5 orbitals are same. As slowly ligands approaching metal atom, energy slowly increases. At one point of time, after reaching close to metal atom, splitting of energy of orbitals occurs. 2 orbitals which are along the axis shows maximum energy. Between the axis shows less energy. So there is energy splitting from average energy line, which is known as barycenter. From average energy line, if you see, 2 orbitals having more energy, here less energy. Experimentally found that from average energy line, the 2 orbitals energy increased, that is plus 0.6 delta O, here decreased by minus 0.4 delta O, that is experimental observed values. Okay. So here you can see octahedral energy splitting, you can specify here delta O is energy gap. You can specify like this also, octahedral energy gap. Octahedral energy gap, so you mention like this, delta O is octahedral energy gap. Okay. And then remaining terms you see here. Crystal field, here we call it as crystal field stabilization energy or splitting energy. Both are same. Crystal field stabilization energy or splitting energy. Anyway, you can define stabilization energy. CFSE. So CFSE formula for octahedral complexes. CFSE is equal to number of electrons in T2G. Number of electrons in T2G here. Minus 0.4 delta O, minus 0.4 delta O plus number of electrons in EG into 0.6 into delta O plus NP. Plus NP. NP is number of electrons in, what is N here? You see here. N is number of extra electron pairs developed due to influence of ligand. Number of extra electron pairs developed due to influence of ligand. What is P here? It is pairing energy. Pairing energy is energy required for additional pairing of electrons. N is number of extra electron pairs developed due to influence of ligand. P is pairing energy, where pairing energy, which is energy required for additional pairing of electrons. Delta O is energy gap between T2G and EG. Okay, it is CFSE calculation formula. Now you see, ligands with NPC donor atoms are strong ligands. Ligands with NPC donor atoms are strong ligands like NH3, CO, where donor atom is a nitrogen, here it is carbon. Strong ligand. Ligands with fluorine, chlorine, bromine, iodine, oxygen, sulfur, these donor atoms comes under weak ligand category. Okay. Pairing energy, it is energy required to cause an additional pairing done by ligands. It is extra energy required to make electrons into pairs under the influence of ligands. So, energy required to cause an additional pairing done by ligands. If strength of ligand increases, energy gap increases. Which energy gap? This energy gap. So, this one. Energy gap between T2 and EG. Delta O is energy gap in octahedral complexes. So, if strength of ligand increases, energy gap increases, CFSE increases, stability increases. CFSE increases, stability increases. So, if strength of ligand increases, energy gap increases, CFSE increases, stability increases. One example I am taking here for better understanding. See, presently we are focusing on mainly on theory content. We are focusing on theory part of coordination compounds. So, after completion of theory part, we focus on numericals. Separate video for the numericals. Okay. I am taking D4, case 1 here, case 2. D4 configuration, any metal with D4 configuration I am taking in the given complex. D4 with weak ligand, D4 with strong ligand, both I am comparing here. Observe it. So, here less energy gap, weak ligand, right? Less energy gap, strong ligand shows more energy gap, weak ligand shows less energy gap. Due to less energy gap, 4 electrons, 1, 2, 3. So, 1, 2, 3. Then 4th electron jump into higher energy level because there is less energy gap here. So, any extra pairs developed here? No extra pairs developed, so hence number of extra pairs is equal to 0. Electronic configuration, question number 1 here. T2G 1, 1, 1 because 1, 1, 1 each. EG, that is 1, 0, so here it is 1, here it is 0, no electron. So, electronic configuration like this you have to write. Okay. CFSE calculation, how you have to do? See. What is the formula? Number of electrons in T2G. How many? 3. We wrote 3. Minus 0.4 delta O plus number of electrons in EG. How many? 1. So, we wrote here 1. Then into plus 0.6 delta O plus 0. Why it is 0? Here N value is 0. So, P value as it is like P substitute. No value given. So, CFSE value is 0.6 delta O. Similarly, same if I apply for D4 case for strong ligand. See, D4 for strong ligand if you apply it. So, what we are going to get? See. Strong ligand, N is equal to 1. Why? Extra pair. See, after filling 3 electrons here, just a minute. Yes, after filling 3 electrons, see 1 electron here, second electron, third electron, fourth electron we filled here. Why? Because of more energy gap, electron unable to jump into higher energy level. Hence pairing occurs in lower level itself. So, the extra pair that is developed due to more energy gap due to influence of ligand. That's why N is equal to 1 because 1 extra pair developed. So, electronic configuration T2G 2, 1, 1, EG 0, 0. CFSE value 4 into, because 4 electrons in T2G, as usual formula 0, EG, how many electrons? EG no electrons, right? 0 into plus 1 into P, so it is the value. So, it is the value in terms of strong ligand, it is in terms of weak ligand. Okay. Here the important point is, in presence of or as a CFSE increases, stability increases. As CFSE increases, stability increases. Negative sign of CFSE indicates that energy is released during this process. So remember, whenever if you see CFSE value -4, -2, remember the one with -4 is more stable. Here only magnitude you need to see, negative sign indicates energy released. The one with more magnitude you have to consider, that is more stable. Okay. Next, strength of ligand. So this sequence you have to remember, strength of ligand, I minus, Br minus, S minus 2. So respective information I gave here. Py is pyridine, Bpy is bipyridine, En is ethylene diamine, remaining you know. So here whatever I kept here in first red color box, these are weak ligands including H2O. So before H2O including H2O, these are weak ligands. Blue color box, whatever I kept here, these are strong ligands. Okay. But one important note, oxalate ion which is C2O4 minus is weak ligand, but with CO plus 3 it behaves like strong ligand. CO plus 3 it behaves like strong ligand. Okay. Observe it properly. Next, case 2. CFT for tetrahedral complex. CFT for tetrahedral complex. Coordination number is 4, sp3. For tetrahedral complex, it is assumed that ligands are approaching metal atom between the axis. Previously, what we wrote octahedral along the axis. Here between the axis, exactly opposite you will get. Hence, energy sequence is opposite to octahedral complex. T2G energy here greater than EG energy. CFSE formula NT2G 0.4 delta T plus NEG minus 0.6 delta T plus 0. See the value NT2G 0.4 delta T plus NEG minus 0.6 delta T. See now. Observe it, NEG minus 0.6 delta T plus 0. So N is equal to 0. None of the ligands is considered as strong for tetrahedral theory because delta T is very low. Energy gap very low between T2 and EG level. So no need to think about N value here. Every time N equal to 0 you can mention. Okay. So here delta tetrahedral energy gap is 4 by 9th of octahedral energy gap. Square planar complexes energy gap between T2G EG is 1.3 into delta O. So which is highest now? Delta SP greater than delta O plus delta T. Highest energy gap observed in square planar complexes. Factors that favors sp3 hybridization. Factors that favors sp3 hybridization. See here now. Weak ligands favors sp3 tetrahedral. Weak ligands favor sp3 because weak ligands less energy gap. Delta T is very low. We know already energy gap in tetrahedral complex is very low. So weak ligands anyway generates less energy gap. So they favor D0, D10, D5 configuration favors sp3 because anyway here there is no participation from D. All are filled when D0 no electron here. Generally these configurations favor sp3 hybridization. Large ligands prefer sp3 hybridization. Why large ligands prefer sp3 hybridization? Because PPH3 like triphenyl phosphine large ligand, in sp3 hybridization there is more angle, large angle 109 degree 28 minutes. Due to large angle we can say less repulsion between ligands. If there is less repulsion between ligands without any interelectronic repulsions or interatomic repulsion, it can maintain stability. So larger ligands prefer sp3 hybridization due to less repulsion because of more bond angle. Metal ions with configuration like noble gases favor sp3. Metal ions with configuration like noble gases favor sp3, like MnO4 minus plus 7, sp3, like noble gas configuration also prefer sp3. It is common hybridization sp3. Okay. Next you see case C. Wherever there is doubt, if you want to go through these points once again, you can pause the video, observe properly the points, listen once again, make notes, then proceed further. Okay. Case 3. CFT for square planar complexes, coordination number 4, DSP2. For square planar complexes, it is assumed that 4 ligands are approaching metal atom along the axis in xy plane. In xy plane, see. In octahedral complexes, we know 4 ligands, 6 ligands present octahedral. But in square planar, only 4 ligands. The ligands above and below, these ligands are removed here. Square planar, above and below ligands are removed. Because out of 6, 2 if we remove, it becomes square planar. So here along the axis they are approaching, but in xy plane. Along the axis they are approaching in xy plane. That's why if 2 ligands along z axis from octahedral shape are removed, it behaves like square planar complex. If 2 ligands along z axis from octahedral shape are removed, it behaves like square planar shape. So if z axis ligands are removed, so z axis orbitals along the axis, z axis orbitals experience less repulsion because ligands are not approaching along z axis. Then orbitals along z axis shows lowest energy in square planar complex. Why? Like octahedral complexes, in square planar complex, 4 ligands approaching along the axis in xy plane because only 4 ligands. Remaining 2 ligands which are along z axis in octahedral complex are removed. So no ligand is coming along z axis, hence z axis orbitals experience lower energy. Out of x square y square dxy, obviously here along the axis these two experience more repulsion, so more energy than dxy. So remaining z axis orbitals lower energy. Okay, like this you see here. So dx square y square, then dxy, dz square, dyz, dxz. Further splitting occurs. Further splitting occurs in square planar complex. First here see EG level, T2G level like octahedral. Then after the further splitting, above and below, dz square, dxy, dyz, dxz. Further splitting. So if you remember the sequence, that's more than sufficient. See, JEE works based on clarity at the same time shortcuts. Entire lengthy method, lengthy theory part if you study without knowing where to stress, no use. So whatever I am pointing here, the important terms where you have to focus, you write those again important points as notes. So that quick revision, much more useful during quick revision. Okay. Here you write one important note. Whenever there is 3D8 configuration of metal, weak ligand combination given sp3. 3D8 combination of metal, strong ligand gives dsp2. 4D8 combination and 5D8, 4D8 or 5D8, whether weak ligand or strong ligand, any combination. 5D8 weak ligand you take, 5D8 strong ligand you take. 4D8 weak ligand, a strong ligand, any combination you will get dsp2 in this case. Okay. So here a regular concept we studied, but now few exceptions, exceptional examples you have to remember here. What are those? See here. Exceptions of square planar are coordination number 4. CuNH3 4 times plus 2. CuNH3 4 times plus 2. Like here it is strong ligand. Cu plus 2. So configuration we know 3D9, 4S0, 4P0, 4D0. 3D, so 9 electrons we showed. But as coordination number is 4 here, coordination number is 4. What it is observed, generally 3D8 plus strong ligand, 3D8 plus strong ligand, according to above given information, here it should be sp3, it should be sp3 generally. But experimentally it is observed that one electron from D transferred to another D, which we call a transference of electron. Hence, D becomes empty, so dsp2. Overall, we are getting dsp2 hybridization here. So, above complex should be sp3 generally. I am writing clearly, see here, it should be sp3, but due to above transference phenomenon, it is behaving like dsp2. So, here what you need to remember, whenever it is given, you remember it as dsp2. dsp2, there is unpaired electron here, that's why it is paramagnetic. So, remember it is dsp2 and paramagnetic because there is unpaired electron. dsp2 and paramagnetic. Okay. Conditions of transference. It's not every time irregularly we cannot show transference. For transference, only strong ligand should be present. Only strong ligand should be present. At the same time, one unpaired electron should be present. Possibility of inner D complex. If there is chance of inner D complex, then in such situations, you can think about transference of electron. Not in all other cases. Okay. So here overall what you have to remember, this complex is exception under. Looks like sp3 because there is no d orbital, vacant d orbital, but due to transference, experimental observed information, transference of electron, it is behaving like dsp2 and magnetic nature is paramagnetic. Okay. See even other exceptions like exceptions of octahedral complex. One example we studied just now. Other exceptions see here. The square planar complex examples, exceptions we studied. One exception CuNS3 just now we studied. So exceptions of octahedral complex. For octahedral complex you see here now exceptions. NiF6 minus 2 generally should be sp3d2, but due to experimental observation, see whenever it is given delta O greater than P, meaning it is giving information about strong ligand. Actually F6 is weak, but it is behaving as strong ligand, experimental information. That's why it shows D2sp3. So what you need to remember, NiF6 minus 2 is D2sp3, but should not be sp3d2. According to regular logic, it should be sp3d2, but observed is D2sp3. This one you have to remember. Similarly, some more exceptions given: FeNH36 sp3d2, MnNH36 sp3d2, COH26 D2sp3, COC2O4. Reason, see wherever I am writing reason like this, it is strong ligand. Reason like this, weak ligand. Behaving like weak ligand, experimentally observed. CuNH36 plus D2sp3. Reason is transference of electron from 3d to 4d. CONO26 minus 4 D2sp3. D2sp3. These exceptions list you have to remember. You can't use logic on this spot for this. You have to remember the data. Pause the video, write the data, then proceed further. Exceptions of tetrahedral complexes. Just now we wrote one example, same I am repeating under together. It should be sp3, but it is dsp2 due to transference of electron from 3d to 4d. CuCN4 dsp2. dsp2. Okay. Next see, keep heading properties of coordination compounds. Properties of coordination compounds. So here magnetic nature, paramagnetic, diamagnetic. Paramagnetic attracted towards magnetic field, diamagnetic repelled by magnetic field. Unpaired electrons not equal to 0, meaning here unpaired electrons present, here absent, n is equal to 0. These complexes shows increase in weight when placed in magnetic field. When placed in magnetic field, they show increase in weight. Why? If you place these complexes in weighing machine where there is magnetic field, because of attraction towards magnetic field, weight of complex, or you can say weight increases overall. Weight increases because it is pulling complex, attracting. Diamagnetic substances shows decrease in weight because they show repel. So here magnetic field repel diamagnetic substance, right? So that's why diamagnetic substances repelled by magnetic field, hence they show decrease in weight, not mass, decrease in weight. Okay. Next, spin-only magnetic moment formula under root n into n plus 2 Bohr magneton Bm. Here mu is magnetic moment symbol, so under root n into n plus 2 Bm. What is n here? Number of unpaired electrons. Okay. Next property, stability of complex. So in different ways you can explain the stability of complex. First, ligand strength. Strength of ligand increase, energy gap increases, stability of complex increases. For example, weak ligand, strong ligand. More energy gap, more stability. So it is stability sequence. Oxidation state, if oxidation state increases, stability also increases. Why? More positive charge, because more positive charge, meaning electron density is more. Electron density, how it is? See, more positive charge meaning less radius. More positive charge meaning less radius, due to which more electron density in given volume, hence it experiences more repulsion from ligand. Energy gap increases and stability increases. Formation constant, metal plus number of ligands, if you join, we will get MLN, which is complex. There is formation of complex. If metal combine with certain number of ligands, it form MLN complex. Equilibrium constant type, it is formation constant Kf. If Kf increases, product increases. If Kf increases, product increases. So then what we can say? Whenever product amount increases, equilibrium constant increases. Here equilibrium constant is Kf, formation constant. Hence, whenever there is increase in product, then you can say product stability increases, or you can say complex stability increases. So write properly here. If Kf increases, product increases, complex stability increases, which is MLN. Which is MLN here, complex. Reverse, if there is dissociation of the same complex, it is complex, coordination complex. Here equilibrium constant is Kd. Kd is dissociation constant. If reaction moving in this direction, so amount of reactant decreasing here. The reactant is our complex here now. So if Kd increases, amount of MLN decreases, hence stability of MLN decreases. So remember, if MLN amount increasing, stability increasing. MLN amount decreasing, stability decreasing. That's what we mentioned. So overall, formation constant directly proportional to stability, dissociation constant inversely proportional to stability. Okay. Next, color of coordination complexes. Color of coordination complexes. So color of coordination complexes, D1 to D9 shows DD transition. DD transition meaning transfer of electrons from one orbital to another. DD transition, transfer of electrons from one orbital to another. Here we know energy gap or delta is equal to hc by lambda, which is h nu, right? See the concept of color here. DD transition meaning transfer of electron from one d orbital to other d orbital. During this transition, certain energy released out, whatever energy released out responsible for color of the complexes. See here now. When white light is impinged on complex, when white light is impinged on complex, or when white light falls on complex, some part of light is absorbed while remaining is transmitted back. Some part of light is absorbed like this. White light is fall on complex. Some part of it is absorbed, some part is transmitted back. The transmitted light responsible for complementary color. Whatever energy released out after absorbing some energy, we call it as complementary. That is responsible for complementary color. So complementary color meaning color what we see. Color what we see is complementary color here. For example, in Vibgyor colors, red color is having maximum wavelength. So red color having maximum wavelength, that is lambda increases, right, in this direction. If lambda increases in this direction, energy decreases. Vibgyor, that is lambda increases, energy decreases. Now, if red color is absorbed, according to given information, if red color is absorbed, then complementary color is green color. How? If red color is absorbed, complementary color is green. If orange color is absorbed, complementary color is blue. If yellow color is absorbed, complementary color is violet indigo combination. Whichever is exactly opposite. See, if green color is absorbed, complementary color is red. Complementary color is the color what we see. Okay. If lambda increases, delta energy decreases, strength of ligand decreases. Here you remember one point, whatever lambda we are writing, it is lambda of absorbed radiation. Lambda of absorbed radiation. Of absorbed radiation wavelength. Stronger ligands absorb radiation of shorter wavelength. Stronger ligands absorb radiation of shorter wavelength. Okay. So now, conditions for colorful or colored property. Absorption of light in visible zone. One condition, it should absorb light from visible zone. Out of visible zone, you will not see any color. D1 to D9 configuration, that is DD transition, one of the reasons. Ligand presence. Ligand should be, so ligand presence, another reason. If ligands are absent, then no DD transition. In presence of ligands only DD transition occurs. D10 is colorless or white, no DD transition in D10 because already completely filled. Few complexes are colorful due to charge transfer. Few complexes are colorful due to charge transfer due to resonance. Not all, few. Here resonance possible, see. So during this process, during this resonance phenomenon, some energy released. Whatever energy released, responsible for the color of the compound. Like these colors, you have to remember charge transfer information. MnO4 minus purple, MnO4 minus to green, CrO4 minus to yellow, Cr2O7 minus to orange, Cu2O, CrO3 purple, orange, and then red. Okay, Cu2O, CrO3 purple when it is dry without any moisture, orange when it is wet with some moisture. Okay, here see some important compounds like brown ring asked in JEE Mains. Brown ring formula, you have to remember. Brown ring FeH2O5NO SO4. FeH2O5NO SO4 minus 2. So here Fe is in plus 1 state. H2O it is neutral, NO is in plus 1 state, sulfate is minus 2. Or you can write, see, instead of writing NO, you can write even NO plus also. So now Fe is in plus 1, it is paramagnetic in nature. Remember, sp3d2 is hybridization. IUPAC name penta aqua, nitrosonium, iron 1, sulfate, which is sulfate. Okay. Now, number of unpaired electrons 3 in this complex. How? Fe plus 1 configuration 3d6 4s1. So 3d6 here 4s1. Here one conditional based hybridization whether it is sp3d2 or d2sp3, in both the cases s orbital required in both the cases, but here s orbital having 1 electron. So to satisfy the hybridization, we need to vacate this s orbital. How we are vacating? Just transfer electron to adjacent 3d. How? You transfer this electron to here, this one. Whatever electron here transferred, here, this one. So after transferring, how many unpaired electrons now? 3 unpaired electrons, sp3d2. Finally, we are getting sp3d2. Condition based hybridization. So this you have to remember. It is sp3d2. Another example, sodium pentacyanide nitrosonium. Sodium pentacyanide nitrosonium. See the formula Na2FeCN5NO plus. Sodium nitroprusside is common name. Sodium nitroprusside, common name. IUPAC name sodium pentacyanide nitrosonium ferrate 2. Why it is sodium? Here sodium. Pentacyanide because 5 cyanide ions. Nitrosonium because NO plus. Ferrate because here iron plus 2 state. Why it is ferrate? Because it is negatively charged. Here there is negative charge. That's why iron 2. D2sp3 diamagnetic in nature. Okay. Remember NO plus is 2 electron donor. NO is 3 electron donor. Information based. Remember NO plus is 2 electron donor. NO is 3 electron donor. In both the cases NO is in plus 1 only. Here also plus 1. Here also plus 1. Okay. Let us see one question here. How to name the compounds where 2 coordination spheres are present? how to name the compounds with two coordination pairs. Like for example, CO NH3 6, CO NH3 twice, NO2 4 3 times. First you find negative charge. Here NO2 is -1, we know. NH3 is 0, NH3 is 0. So -1, NO2 4 here -1. So -1 how we can consider? 4 NO2 minus, so 4 into NO2 minus into 3 because it is thrice. Total negative charge is -12. If total negative charge is -12, total positive charge should be +12. Then how we can distribute? Both are cobalt, its common state is +3, here also common state +3. +3, here +3 into 3 times. So here 9 plus 3, 12, also, here also you will get 12. Okay. So now among these, which is cation here? Cation is here cation is +3, here anion is -3. So first we have to write cation. Hexaamine cobalt 3, hexaamine cobalt 3, here see for example, hexaamine cobalt 3 and diamine tetranitrito N. Hexaamine cobalt 3 and then diamine, see diamine nitrito cobaltate 3, cobaltate 3. Okay. So along with that, some common coordination number of metals. Some common coordination number of metals I gave here. See, Cu plus 2 4, Ag plus 2. See here, this you need to remember. See once, observe everyone. Cu plus coordination number, Ag plus existing coordination number 2. Platinum plus 2, Pd plus 2 always 4 square planar. Pd plus 4 always 6. Nickel plus 2 4 or 6 coordination number. CO plus 3, CO plus 2, or you can say Cr. Okay, these whatever mentioned, they exist in 6. Here Pd plus 4 also 6. You note it down, this one, because sometimes required, sometimes application type questions, these coordination numbers, common coordination numbers required. One more, see, mention the formula of iron 3 hexacyanide C ferrate 2. Here this time they gave IUPAC name. They gave IUPAC name. Now we need to write IUPAC formula. Iron 3 plus 3, hexacyanide 6 Cn, ferrate, so iron plus 2 here they mentioned. So how to do? You write here Fe plus 3, FeCN6 minus 4. Why it is minus 4? Because 6 into minus 1. Iron is plus 2. So overall minus 4 charge. After showing charges, now we crisscross it. Just interchange. Here 4 becomes Fe4. 3 becomes thrice. So it is the formula. It is the formula of the compound whatever given. Okay. So that is about, we studied here till overall about some important compounds, like even properties of coordination compounds, exceptional list we studied, some important repeatedly asked JEE Mains questions. How to write name if they provide two coordination complexes, or if they provide IUPAC name, how to write compound formula. So everything we discussed here. Once everyone watch part 1, then come to this part 2. Okay. So be clear about these two parts, part 1, part 2. Next we are going to discuss about part 3, where isomerism, the most important topic, where most of the students get confused. Okay, don't worry, in simplest crystal clear way we are going to discuss in upcoming part 3 video. I hope everyone clear with the concepts, part 1, part 2. Soon I will come with part 3. Meanwhile, you complete these two parts and solve relevant questions. Okay, thank you very much.